recall what we have been defining in lecture 1. Last we have ended the lecture 1 with the definition of a vector space. So, let us recall a definition once more. To define a vector space, we need a field. So, I will always start with let K be a field. Then definition, an abelian group V plus is with a scalar multiplication of K on V, which is a map from K cross V to V, which the image of the pair A comma V, I will denote AV, satisfying the following properties. There are 4 properties, if you recall. These 4 properties are basically the properties about compatibility of the field structure on K and these addition on V and the scalar multiplication on V. So, the 4 properties are A B times V same as A B V, where B V is a scalar multiplication and A is a further scalar multiplication on the new element B V. On the other hand, we multiply A and B in the field and then take a scalar multiplication on V. Similarly, with the addition of first addition of the vector space, that is A times V plus W equal to AV plus AW, and third one is when you add elements in the field A plus B times V equal to AV plus BV, and last one is 1 times V equal to V. This property should be valid for all scalars A, B in K and all elements V, W in V. So, if an abelian group has a scalar multiplication of K and it satisfies these properties, then an abelian group with scalar multiplication is called a K vector space. Or also sometimes I will say vector space over K. This field is called K, will be then referred as scalar fields, scalar field of V, and elements of K are called scalars. Elements of V are called vectors. Later on we will see that how this concept is related to the older concept of the vectors in geometry. Today I want to give many examples, many different examples which will be constructed from the given ones. So, recall that yesterday the model example I gave was k power n, Cartesian product of k n times. So, elements of these are tuples, these are n tuples with coordinates in k. And we saw it is a vector space in a very natural abelian group structure, namely the component wise addition which is coming from k, addition is component wise, and scalar multiplication is also component wise. Also component wise. So, the multiplication the addition of the field k is extended to the set of tuples, and multiplication in the field k is also extended as a scalar multiplication on these tuples. And later on we will see that every so called finite dimensional vector space will look like this. But before I go on, I want to mention some of the properties that one need to check. I will just mention them without proofs. For example, general distributive law. This is a generalization of the property 2 and 3 sort of. So, that is, if you have finitely many elements ai, I in I, this I is index set and finite. Typically one will take I equal to, for example, 1 to n, 1 to m set with m elements. But sometimes it is useful to denote or enumerate the number the elements in I differently. So, for that reason we will not in general assume that I is 1 to n, but we will assume I is a finite set, it has only finitely many elements, and cardinality is some natural number m. So, cardinality is some m. And suppose you have finitely many vectors Vj, j in j, again j is index set, finite index set. So, for example, j could have n elements which one might denote as j1, j2, jn. Finite is important because without finite the statement will not make sense. So, on one hand we have this summation ai. So, we are adding elements AIs, the finitely many elements, are we are adding them in the field. So, you get again an element in the field. So, you get a scalar. So, this is a scalar, and we have seen that creativity. So, this is well defined, it does not matter where we put the bracket. So, this sum is well defined because of the associativity in the field. So, this and from the vectors Vj we will sum them up in by using the addition in the vector space. So, you will get a vector. So, this is a vector, and when I take the scalar multiplication, and now what do we get? What I want to stress is we can open up the bracket, So, that means we are using the property 2 and 3 repeatedly. So, we can write this as summation now over I comma j in the product set ai Vj. So, this needs a formal proof. When I has 2 elements, j has 2 elements, then it is precisely either 2 or 3. So, I will leave it for you to prove this. So, this is known as general distributive law. That means you can use the distributivity as many as times you want. More important is finitely many times, because infinite sums do not make sense in general in the vector spaces. Okay, another sort of, these I call it sign rules. When one makes a calculation with formulas, we will obey this. So, for example, you have 0 in the field, 0 scalar also we are denoting the same notation, and 0 vector also we are denoting by the same letter 0. So, it should be clear from our context what we mean. For example, 1 I want to write 0 times x. As I told you earlier, scalars we are denoting by the letters a, b, c, etc. Vectors we are denoting by x, y, z, u, v, w, etc. So, here 0 is a scalar, x is a vector, because we cannot multiply vectors. So, this result should be 0, and the 0, this should be vector. Now, on the other hand also I can take like that, any scalar a and multiply the 0 vector, then I should get a 0. So, this is also 0. So, I could write the equality here, because this 0 is a vector. So, one needs to prove this. So, second one, if I take any scalar a and multiply by negative of the vector minus x, negative of the vector simply means inverse in the abelian group of x. So, this should be same as you take the scalar and take the negative of that, that means inverse in the additive group of the field, and multiply by x. This result should be same. Or also you could also take this, you take the scalar multiplication of a on x and take the negative of that vector. All these three quantities should be equal. Okay, another one, third one, minus of the scalar, negative of the scalar times negative of the vector is same as scalar times the vector. Fourth is, if I take scalar and take the scalar multiplication with the difference vector, that should be same as ax minus ay. This is the vector subtraction, and same thing with the subtraction of the scalar, a minus b times x should be equal to ax minus bx. So, these rules are so natural that, and they will also simplify our writing, which will be exactly same as what we were doing with our number systems. So, proof, I will leave the proof to the, so I will simply say verify. This will give you a good practice about how does one write the equations in a abelian group or in a vector space and so on. More important I want to say is the following cancellation rule. And this time we will prove it. Suppose, so let a be a scalar and x be a vector, then if a times x is 0, then either the scalar a is 0 or the vector x is 0. So, let us write a proof. So, we want to prove either or statement. So, always in mathematics you assume one of them is not true and prove the other is true. So, suppose a is not 0, then we must prove that x is 0. We have given ax is 0. When you multiply this equation by a scalar a inverse, because a is a non-zero element in the field, a inverse is also an element in K, that is why we have defined our fields. So, this will imply A inverse times Ax equal to A inverse times the vector 0, which is 0. Just now we have wrote the sign rule 1, for example. On the other hand, this A inverse times Ax, we can use the property 1, which will say that I can first multiply A inverse and A in the field and times the vector x. This is by property 1. Only in the beginning I will write this, after some time I will not write this. But this is same as, because A inverse is the inverse of A in the field, this is same as 1 times x. But property 4 says 1 times x is x. So we have proved x is 0. So this proves x is 0. So this cancellation rule says that if your scalar multiple of a vector is 0, either the scalar is 0 or the vector is 0. This was intuitively clear when we studied the vectors. Okay, next. Okay, now let me give lots of examples of vector spaces. So examples. First one. So in all these examples, when I don't mention anything about the letter k, we will always take k to be a field, an arbitrary field. It could be finite, it could be infinite. It could be our rational field of rational numbers, or field of real numbers, or field of complex numbers, or a finite field with p elements. Okay. So the first example, let I be any set. So this example is generalization of our prototype example, which k power n. So here I would like to mention k power n also you can think, either you can think the elements are tuples, or you can think they are mappings from the set 1 to n to k. This is the set of all maps from 1 to n to the field k, maps. So this correspondence is usually either you think of function f, or you think of the tuple f of 1, f of 2, f of n. Each tuple will give a unique function, and each function will give a unique tuple. So when a set is infinite, or you do not know beforehand what the set, how many elements it has, etc., it is better to think about functions from I to k. So that is what I am considering here, k power I. This is the set of all maps. Sometimes I will write this also, maps from I to k, or like this, f from I to k, if f is a map. Also I will like to take this opportunity about my saying sometimes. So the difference between the function and a map, there is a very fine distinction between these two words, and most of the people in general they do not do this, but I would like to do this for many reasons. Function means where the values are, that is one of our number system. For example, it can be rational number, it can be real numbers, it can be complex numbers. When we do not know about the field, then we will call it a map, when the values where it goes. If it is our known set, like one of the number system, then we will call it a function, otherwise we will call it a map. So that is the reason I am writing a map here. If k was set of real numbers, I would have said function. So our V is now k power I, and I want to check that this V is a vector space, k vector space, in a very natural way. So that means I need to define a addition operation on these maps and get a map again, and with that addition it should be an abelian group, and also I should tell you what is the scalar multiplication, and then one need to check all those 4 properties of the vector space. So, things are very natural, as you will see. If you have f and g, 2 maps from I to k, then I need to define what is the plus f plus g, and this the result should again be a map from I to k. So, that means I need to define what is f plus g on arbitrary element of I in I. And what can we do? Obviously, on one hand we can take f of I, which is an element in k, also we can take g of I, also element in k, and add them, use the addition in k. So, we have added these values. So, result is again an element in k, because k is a field. So, I define this f plus g evaluated or image of I under f plus g is take f I, take g I and add them in the field. So, you get a map from I to k. Now, I need a scalar multiplication. So, if I have a scalar a in k, then I need to define what should be a times f, and this should again be a map from I to k. So, I need to define what is a f evaluated on I. Well, what do I have? I have f of I, this is an element in k, and I have a given element in a in k. So, I can multiply in the field. So, the result I will get a product of 2 scalars, which is again a scalar. So, it is again an element in k. So, with this I have defined plus on V, and also I have defined a scalar multiplication. Now, see, these 2 operations are so very natural and canonical that all the properties of the vector space are satisfied, that again I will leave it for you to check. So, I will just mention. So, I will just first mention, check that with this operations V equal to k power I is a k vector space. Notice that if I take f in k power I, the negative of that is that map I to k, which maps I to f of I and minus of that. This is that map, and it is obvious that this serves the purpose for the inverse. So, that with respect to plus it is indeed an abelian group. Okay. So, for example, let us take special cases. For example, if I were a singleton, then what is k power singleton? 1. This is nothing but just k, a copy of k, because you are taking k cross k cos 1 time. So, it is only one copy, and the vector space structure here is nothing but the field structure. So, vector space structure is exactly same as the field structure. So, when one says a vector space structure, that means 2 things. One is that addition of the vectors and the scalar multiplication. With those 4 properties. All these together is called a vector space structure on V. The plus gives an abelian group structure, scalar multiplication gives a scalar multiplication, and the 4 properties combine them too. Okay. So, k equal to I equal to say 1 to n, or any set I who has exactly n elements, then k power 1 to n is nothing but k power n, which was the prototype of the example that we have mentioned in the before the definition of the vector space. So, these examples are also called function spaces. Function spaces because here vectors are functions. So, elements in k power I are functions. This, strictly speaking, I should use this word only when k is q, r or c. That is the reason why they are called function spaces. And you will see these examples more often in your analysis courses. Okay. Now, example 2. This is what I am addressing to what is called restriction of scalars. So, typical situation will arise when we are given a field k and a vector space V, k vector space. For example, V equal to Rn, R power n, here k is R, field of real numbers. Such vector spaces are also, people call them as real vector spaces. If the field is C, then one calls them as a complex vector spaces. So, it is clear from the writing what scalar field one takes. Sometimes it is useful to take complex numbers as scalars, sometimes it is useful to take real numbers. Okay, so, this is a field, so this is a real, when you have given a real vector space, for example, that is a V equal to Rn, and but this field of real numbers contains the field Q, and the Q is actually a subfield of R. Subfield simply means that when you restrict the field structure of R to the subset Q, it should give the Q vector space structure. Q, you should get the original field operations in the Q. That is because we have extended the plus and multiplication from Q to R in a very natural way. So, it is a subfield. So, one would like to consider this real vector space as a Q vector space. So, what do we have to do? Already we have given an abelian group structure that will not change, only we have to give a scalar multiplication of Q on V in a very natural way. So, scalar multiplication of R is given. So, R cross V, to V we have given a scalar multiplication. I simply restrict, and there is a subset here Q cross V. So, I simply restrict the scalar multiplication to Q. So, restriction I will just restriction of the scalar multiplication to Q simply means you take this scalar multiplication, given scalar multiplication map and restrict to this set. So, you get a map from Q cross V to V, and with this already the properties are satisfied. So, with that it becomes, this V will become a Q vector space. And there is nothing special about Q and R. In general, you could take arbitrary field K and a subfield. As I said, subfield should mean that when you restrict the field operations of k to k prime, they should get the operations of the field k prime. In that case, every k vector space you can think k prime vector space. Yeah, before I stop for the break, I would like to mention here in particular, it is important case. So, I want to record it here. In particular, obviously C is a C vector space. If like in our earlier example n equal to 1 and R is a subfield of C. So, the same C I can think as C as a R vector space by restriction, or I can also think C as Q vector space. So, here the scalars allowed are rational numbers, here the scalars allowed are real numbers, or even also R is a R vector space, then it is also Q vector space by restrictions. But here I cannot say R is a complex vector space, because to extend I need to do more. For restriction I do not have to do anything, I have to just simply restrict. Okay, so I stop here and we will come back after a few minutes.